Hello my friends and welcome back to the You Can Do TV channel. The wheel may appear ordinary, yet the effort required to bring it to life turns manufacturing into something awe-inspiring. In the workshops of Hartung, wheel production begins with design and engineering, where load capacities and geometry are calculated with great accuracy. Only then can raw steel plates enter the line. The first transformation happens through stamping presses that cut and form discs. Immense forces shape the metal into profiles capable of handling over 120 kilonewtons of stress. Next, cold rolling machines, such as those from REPKON, extend the rim diameter to more than 22 inches. Observing steel flow under controlled pressure shows how raw material becomes a structural component. Assembly continues with robotic manipulators, including FANUC systems, which weld and align parts with consistent quality. Operators monitor every stage, measuring radial runout so no wheel leaves the factory without passing strict inspection. Once geometry is approved, surfaces are treated through cataphoresis coating, giving corrosion resistance and long service life. Finally, wheels are painted or primed, ready to carry trailers weighing up to 80 tons. Watching steel evolve into a product this durable sparks admiration for the skill, discipline, and responsibility behind industrial manufacturing. At first sight, a steel rail might look like nothing more than a long bar of metal, but its production reveals a demanding process shaped by heat, force, and timing. The journey begins with 280 by 400 millimeter blooms, prepared in the steelmaking plant and selected according to the rail type. They are reheated in walking beam furnaces until they reach about 1200 degrees Celsius. This stage already shows how energy-intensive rail manufacturing is and how every ton of steel must be guided with care. Once heated, the blooms pass through a sequence of 5 rolling stands. Each pass stretches and compresses the steel, gradually shaping it into the recognizable rail profile. The sheer scale of machinery and the synchronized rolling operations make this stage striking, especially when 2 final stands must work in perfect alignment across a distance of nearly 100 meters. Cooling follows on a 130-meter walking beam bed. Rails are not placed in a straight line but slightly pre-bent, compensating for uneven cooling between the rail head and foot. This clever step prevents unwanted distortion. Finally, straightening machines and non-destructive tests confirm geometry and strength. Watching a 120-meter rail reach completion is both technical and impressive. On the surface, a pipe fabrication shop may seem straightforward, but the process inside reveals complex workmanship. Production begins with material selection and layout planning to match system specifications. Pipes are cut, beveled, and bent as needed. Welders join segments and fittings, forming spools ready for installation. You sense the rhythm of spools taking shape as molten metal bonds each section. Inspections follow with measurements and pressure testing to ensure integrity. Completed assemblies are tagged, stored, and dispatched to job sites for final installation. Observing how raw lengths evolve into reliable piping systems brings deep appreciation for the craft and technical insight driving every connection. A sense of dedication fills the room, as every copper sheet awaits its transformation into a durable pot. The workshop is a space where experience meets material, and each step reflects the craftsman's commitment. Each sheet is thick and resilient, able to endure the mechanical forces required to form a precise shape. Once prepared, the sheet is mounted on a rotary milling machine. The metal rotates steadily, while the craftsman guides tools to gradually shape it into a round form. Every movement is deliberate, a balance between machine speed and human touch. The copper yields smoothly under gentle but firm guidance, taking on its circular structure. Small adjustments are made continuously to perfect the symmetry of the pot. Watching the metal gradually curve into shape reflects both patience and expertise. The copper bends evenly under constant attention, forming the body of the pot. The process is repeated, refining curves and edges, ensuring uniform thickness throughout. The subtle variations in pressure highlight the skill and experience involved. Minor adjustments are applied as needed, demonstrating careful observation and adaptability. Each refinement brings the piece closer to its ideal form. The pot embodies not only practical use but also the craftsman's passion and mastery. Even in routine steps, creativity and care are evident. The workshop atmosphere inspires respect for the craft. Tools, though simple, are extensions of skill. Each step celebrates the harmony of material and technique. The finished pot stands as a symbol of tradition maintained in modern practice. The clang of metal fills the recycling yard, as discarded aluminum wheels arrive for processing. At the start, workers place the wheels onto a feeding conveyor, guiding them toward the hammermill shredder. The atmosphere is intense, with every move showing industrial strength. Inside the shredder, rotating hammers powered by 160 kilowatts motors smash the wheels into fragments. This action reduces bulky castings into manageable scrap pieces, ready for further handling. The shredded aluminum exits through screens that ensure uniform size before collection. Conveyors then transport the processed metal toward sorting and storage. Efficiency here is remarkable, as tons of material move swiftly through the system. Operating this line requires only 1 to 2 workers, making it practical for recycling yards. It is impressive how productivity rises with such minimal manpower. The company highlights its long-standing focus on recycling technology, yet the machinery itself demonstrates the true value. At the heart of Novantia's S-80 submarine lies its AIP system, engineered for weeks of submerged endurance. Diesel generators supply power, while the fuel processor converts liquid fuel into reformate gas for the fuel cells. CO2 disposal ensures low signature, supporting stealth and reliable operation beneath the sea. All focus turns to the Nargisa PC-16 hot forging machine, where a heated steel bar is readied for transformation. A solid piece of steel is heated and secured with a hydraulic clamp. With the cycle activated, the material is pressed and rolled into a tight spiral tip. Adjustments in stroke length and pressure adapt to different bar sizes, while operators follow every step closely. The machine forges up to 4 pieces per minute, each cycle lasting about 10 seconds. Watching red-hot steel twist into decorative forms is both powerful and captivating. Inside the Conroe facility, production begins with steel plates unloaded and transferred for fabrication. Large plasma arc machines cut the plates into specific dimensions, their arcs sparking across the surface. Operators ensure every cut follows the engineered design. Next, the cut pieces move through drilling and punching stations, forming the connections required for lattice tower assembly. Automated handling reduces excess lifting and keeps materials flowing efficiently. One can sense how speed and accuracy blend in this process. The workflow is designed to maximize throughput while minimizing material waste. Supervisors check each station to ensure optimal performance and prevent delays. Fabricated members then enter welding and inspection areas. Here, strong joints are made to withstand the stress of high-voltage transmission. It's striking to see strength being built step by step. Quality checks confirm that alignment and weld consistency meet standards before advancing. Galvanizing follows, with components dipped in a 450 degrees Celsius bath of molten zinc inside an enclosed treatment building. Fumes are fully captured, making the process environmentally safe. The glowing surface after dipping reflects both durability and protection. Finally, tower sections are bundled and prepared for shipment across North America. The sound of grinding sparks introduces the making of a bevel gear, an essential component in countless mechanical systems. In this process, the focus is on dry cutting, a method that eliminates the need for lubricants, while still delivering clean and efficient results. It's striking to see how the process achieves accuracy without oil. The operation begins by setting up the bevel gear blank onto the cutting machine. With the blank secured, the system aligns the tool at the exact angle needed for the gear's tooth geometry. The alignment step alone highlights how demanding gear production can be. Next, the cutting tool engages the blank, shaping each tooth with high-speed motion. Because this is a dry process, the machine relies on optimized cutting speeds and tool material to prevent excessive heat buildup. You can almost sense the intensity as sparks fly across the gear surface. Each pass brings the gear closer to its final profile, with edges formed sharply and consistently. The sparks cascading off the tool look both powerful and controlled. Once all teeth are cut, the gear shows its distinct bevel profile. The geometry ensures that it can transfer torque smoothly at an angle, a feature critical in automotive and industrial applications. The finished gear carries a strong sense of purpose in its design. Before leaving the machine, the gear is inspected to confirm uniform tooth depth and alignment. Watching the piece go from blank to functional gear feels truly impressive. Intense heat radiates from the ring as the rolling process sets in motion. Heat-treated stock is first placed on the forming platform. Hydraulic rollers then press against the metal, expanding its diameter while maintaining thickness. Parameters entered in advance control the entire process. Each turn pushes the ring closer to its final dimensions. One can almost sense the immense pressure involved. What makes sand casting compelling is not just the method, but the sense of progress, as each action brings material closer to utility. Each step reveals the quiet mastery of workers shaping metal with intention and care. In this workshop, aluminum becomes the central material, chosen for its lightweight strength and reliable casting properties. Sand molds provide the foundation, holding the liquid metal in shape until it solidifies. The intensity of the furnace seems to energize the entire workshop, inspiring focus and precision. Every mold prepared reflects the skill and experience accumulated over years of work. The way workers coordinate to handle multiple molds at once shows remarkable teamwork. Subtle variations in sand density are monitored to ensure uniform casting quality. The process starts with the preparation of molds. Workers arrange fine sand mixed with binding agents, ensuring each cavity matches the desired form of the product. Patterns are pressed into the sand to create negative spaces, then carefully lifted out. Channels and vents are added, allowing molten aluminum to flow smoothly. It feels like every grain of sand has a purpose, reinforcing how much detail goes into each stage. The molds are then closed tightly and secured, ready to receive the molten stream. Even small adjustments to vent placement can affect the quality of the final casting. The video highlights the key stages involved in producing precision aluminum components. The glow of liquid metal immediately draws the eye, hinting at the intensity of the work ahead. Aluminum ingots are melted in high-capacity furnaces until reaching the correct temperature for casting. Once ready, the liquid metal is poured into precise dies, forming complex shapes with efficiency and strength. It is fascinating to observe how the flow of molten aluminum fills each cavity perfectly. The coordination between operators and automated systems ensures each component meets exact design specifications. After casting, the parts are cooled rapidly and ejected from the molds. Excess material, known as flash, is trimmed, leaving clean, functional components. Operators inspect dimensions and surface quality to ensure each piece meets strict requirements. Occasionally, adjustments in mold temperature or pouring speed are made to maintain consistency. Machines handle repetitive tasks, but human oversight ensures any subtle flaws are corrected. Some components undergo secondary treatments, such as machining or finishing, to achieve final specifications. The rhythm of the production line shows how modern engineering balances automation with skilled supervision. The precision achieved in each cycle reflects both advanced equipment and experienced operators. Completed parts are then sorted and prepared for shipment, demonstrating the careful planning behind industrial die casting. Every finished aluminum component embodies both durability and the expertise poured into its creation, ready for use in demanding applications.
In the workshop, steam rises as raw ceramic pans are prepared for coating. The initial step involves dipping each pan into a liquid mixture that forms the non-stick layer. Observing the uniform coverage, one can appreciate how consistent results are achieved across multiple pieces. The process has an almost hypnotic rhythm as machines move pans in and out, ensuring each surface is treated thoroughly. After dipping, the coated pans are transferred to a conveyor that guides them into a high-temperature oven. Here, heat solidifies the coating, bonding it tightly to the pan body. The glowing interior of the oven emphasizes the intensity of this curing stage. It is fascinating to see raw material gradually gain the durability that will make it last in kitchens for years. Temperature controls and timing are critical here, preventing imperfections in the finish. Workers monitor the flow closely, adjusting speed or position when needed. Once baking is complete, the pans are allowed to cool briefly before being visually inspected. Every curve and edge is checked, reflecting the care invested in each product. Any inconsistencies are noted for adjustment in subsequent batches. Following inspection, pans move to packaging, ready to leave the production line. The efficiency of this operation highlights the harmony between human oversight and automated handling. It's remarkable how simple raw shapes become functional kitchen tools. The journey from uncoated clay to finished cookware combines chemical reactions, heat, and skilled coordination. By the end, one sees the full cycle of ceramic cookware creation, a testament to both engineering and craft. Watching these pans progress evokes an unexpected sense of admiration for industrial artistry. The raw steel sheets promise durability as they line up for shaping into 200L drums. The process opens with flattening thick steel coils, ensuring uniform thickness across every sheet. Observing this stage, one appreciates how raw material consistency is vital for durability and leak-proof performance. The steel passes through straightening rollers that remove minor bends and warps, a quiet yet critical step that ensures each drum maintains structural integrity. Cutting follows, where CNC-guided shears shape the sheets to precise dimensions. Each cut is exact, setting the stage for consistent assembly and seam alignment. It's remarkable how technology controls such massive materials with exacting detail. The edges are then flanged using hydraulic machines, forming the characteristic lip that will later accommodate the drum's top and bottom ends. Watching the flanging press compress steel with such force is awe-inspiring, illustrating sheer mechanical power meeting controlled design. Next, the sheets advance to the cylindrical forming station. Here, rollers bend the panels into seamless cylinders, with technicians monitoring alignment to prevent any deformation. Once formed, the drum bodies are welded along vertical seams, producing a robust, airtight structure. Post-welding, they undergo grinding and surface inspection to remove imperfections and confirm uniformity. Finally, each drum body is stacked and sent to the next stage for end attachment and coating, ensuring longevity and compliance with safety standards. The workflow highlights industrial discipline, precision engineering, and human oversight combining to produce 200L drums ready for commercial use. Observing this sequence, one gains insight into both the scale and care behind seemingly simple containers. The path to uniform, high-quality copper strips starts with these substantial billets entering the rolling sequence. These metals are heated and passed repeatedly through rollers, reducing thickness and creating uniform sheets. It is impressive how raw metals gradually transform into precise strips with smooth surfaces. Cold rolling follows, enhancing hardness and surface finish. Finished strips are inspected, cut to specifications, and prepared for shipment. The process highlights mastery over temperature, pressure, and metal behavior in every stage. Scrap metal is reborn as durable stainless steel ready for industrial use. At the start, old sinks, pots, and other steel waste are collected and loaded into a furnace. Nickel and chromium are added to the mix, enhancing strength and corrosion resistance. Electric arcs heat the mixture to extreme temperatures, creating a spectacular boiling effect that looks almost like fireworks. After hours of intense heating, the molten metal is transferred to a refining furnace where argon and oxygen are introduced. Impurities react and separate, forming slag that is removed, while metallurgists continuously monitor temperature and sample the mixture to control chemical reactions. Adding scrap during boiling increases the volume and accelerates the reaction, ensuring a uniform alloy. Once refined, the molten steel is cast into ingots or slabs. A steelworker marks each piece with a special pencil that writes on the glowing metal, keeping track of production batches. These slabs are then reheated to soften the metal, while surface oxides and rust are washed off with high-pressure water. Rolling mills stretch and flatten the steel, gradually increasing its length while cooling it with continuous water sprays. The extended strip reaches lengths of approximately 600 meters and is slightly cooled to maintain flexibility for coiling. The steel coil is then treated with hot acid, removing remaining rust and residues. The material is slowly heated and cooled to relieve mechanical stresses and improve workability for further processing. Subsequent rolling brings the sheet to the desired thickness, closing surface pores and giving the steel a bright finish. Chromium in the alloy reacts with atmospheric oxygen, forming a protective oxide layer that prevents rust. Every stage reflects a combination of heat, chemical control, and mechanical effort. Observing these processes highlights the transformation of raw or recycled materials into durable, corrosion-resistant stainless steel. The sequence demonstrates the skill of metallurgists and the efficiency of modern machinery, producing sheets that meet both structural and aesthetic requirements. Even in industrial scale, the workflow captures the interplay of temperature, force, and chemical reactions, revealing the fascinating complexity behind everyday stainless steel products. A massive railway crane stands ready, its hydraulics primed for heavy lifting along the track. The multitasker showcases its multi-purpose design, capable of handling switch construction, track laying, bridge support, and accident recovery with remarkable efficiency. Observing its movement, one is struck by the balance between raw power and controlled operation. The process begins with positioning the crane precisely along the rails. Operators secure stabilizers to ensure safety while heavy components are moved. Hydraulic arms extend smoothly, lifting rails, sleepers, and structural elements with ease. Each attachment, whether a hook, grab, or spreader beam, is selected according to the task at hand. During switch construction, the crane maneuvers components into exact alignment, allowing crews to fasten parts with minimal delay. Track sections are lifted and placed over sleepers, demonstrating the device's capacity to manage both weight and precision. On bridge-related operations, the crane supports beams and girders, while coordinating with ground teams to ensure proper fit. Accident recovery tasks reveal another dimension. The multitasker can remove derailed carriages or debris without endangering personnel, showcasing flexibility under demanding conditions. The synergy of hydraulics, operator skill, and mechanical engineering creates an impressive display of coordinated motion. Each task reinforces confidence in the machine's reliability and versatility. As components are lifted, aligned, and secured, the crane's presence transforms challenging railway work into an organized and efficient operation. The multitasker embodies the combination of strength, adaptability, and intelligent engineering needed in modern railway maintenance and construction. Molten iron flows into prepared molds, where robotic arms and sensors guide the casting process, ensuring shape, integrity, and future reliability. Giant presses loom over stacked steel sheets, poised to mold heavy metal into engineered perfection. The BL5S 1800-ton Versen mechanical press rises, its 54-inch by 312-inch bed ready to handle extreme force. Operators monitor the setup, ensuring correct alignment and adjustment of the 12-inch shut height. As the stroke begins, metal yields under controlled pressure, folding and forming exactly to specifications. The rhythm of the press echoes through the workshop, emphasizing both power and control. Nearby, the 2,000-ton Bliss mechanical press engages its 724-inch by 240-inch bed, adjusting the shut height to 62 inches, preparing for another cycle of heavy deformation. Observing the synchronized operation of these presses evokes admiration for engineering ingenuity. Every stamped part carries the mark of immense force guided by technical mastery. The workshop hums with energy, where steel, motion, and human oversight converge. Energy pulses through machines, bending, cutting, and threading steel into bolts ready for action. Raw material enters the 360-degree straightening machine, where each steel rod is aligned perfectly for processing. The aggregate conveyor carries the straightened rods toward the crocodile-type hydraulic cutting machine, which slices each piece with consistent force. The cutting force is calibrated to accommodate various steel diameters without deforming the rods. It's impressive to see how uniform each cut becomes, a testament to machine power and design. Next, numerically controlled sizing machines measure each rod to exact specifications, while the hydraulic bevel angle cutting adjusts ends for precise assembly. Sensors continuously monitor rod length and bevel angle, ensuring zero deviation from the programmed parameters. The combined type hydraulic necking machine then shapes the bolt ends, preparing them for threading. Each bolt seems to grow under the mechanical rhythm, taking form with unstoppable momentum. Thread rolling is carried out by hydraulic rolling machines, producing deep, durable threads that promise strong fastening capability. The rolling pressure is optimized for each bolt grade, creating threads that meet strict industrial standards. Automatic screw machines of combined nuts add nuts efficiently, while damping nut bolts are transferred directly into the next station. Full automatic punching and pin machines drill holes with remarkable speed and accuracy. Strapping and finishing machines organize the bolts for packaging, while the automatic steel strapping machine secures bundles for transport. CNC stack cranes then carefully lift and position completed bolts. Each stack of finished bolts reflects the seamless coordination of complex systems. The rhythm of this production line is almost hypnotic, each machine synchronized like parts of a large mechanical symphony. Throughout, the electric, hydraulic, pneumatic, and automation control systems work in unison, ensuring high-speed, continuous production of various bolts, including round steel and screw thread types. Every stage reflects engineering precision, yet there's an observable elegance in the efficiency. The sequence demonstrates how technology, when applied with skill, transforms raw steel into reliable, standardized anchor bolts, ready for construction and infrastructure projects worldwide. At the end, finished anchor bolts are neatly stacked, each one a product of careful orchestration of modern machinery. Observing the workflow gives a sense of respect for the harmony between mechanical power and process design. It's a powerful reminder of how industrial systems can achieve both productivity and reliability. Sparks fly as raw metal meets the force of the massive press, shaping the future tire parts. The descaling process removes surface impurities, ensuring a clean start for pressing. Press forging shapes the metal under immense force, compressing it into basic tire forms. The rolling mill then elongates and refines the forged blanks, preparing them for heat treatment. Transfer tunnels move the parts efficiently toward the furnace, where heat treatment hardens the metal. Quenching follows, locking in structural integrity and strength. Cutting machines then trim tires to precise dimensions, while laboratory samples are taken for tensile, impact, and chemical analysis. Metallographic inspections reveal microstructures, and automatic ultrasonic controls detect hidden flaws. Hardness tests confirm durability, and machining prepares tires for final assembly. Magnetic particle inspections, along with visual and dimensional checks, ensure each piece meets stringent standards. Finally, painting, protective coating, and packaging ready the tires for transport. Industrial ingenuity takes shape in the Texas machine shop, where advanced CNC machinery tackles complex metalworking tasks. The session opens with large aluminum and steel blanks loaded onto a twin-spindle CNC lathe. Each workpiece is precisely secured, setting the stage for simultaneous turning operations on both spindles. Observing the interplay between dual turrets and live tooling, one appreciates how multiple cuts are achieved efficiently, reducing cycle time while maintaining tight tolerances. The first cuts reveal the transformation of solid stock into components with intricate geometries, highlighting the importance of spindle speed, feed rates, and tool selection. The choice of carbide inserts allows high-speed cuts without sacrificing surface integrity, while adaptive feed strategies optimize material removal rates. Tool wear is monitored in real time, enabling predictive adjustments before precision is affected. Once primary turning operations finish, the lathe transitions to drilling, threading, and milling tasks using live tooling attachments. The cutting fluid circulates continuously, keeping tool temperatures stable and preserving dimensional accuracy. Each pass of the cutter removes precise amounts of material, gradually shaping complex features such as internal bores, slots, and threaded holes. It is impressive how the integration of multiple turrets and spindles allows simultaneous machining on different faces of the part, increasing efficiency without compromising surface finish. Chip evacuation systems ensure debris does not mar finished surfaces, maintaining tight tolerances. High-frequency vibration analysis confirms spindle alignment throughout heavy cuts, preventing deflection errors. Next, parts are moved to the horizontal boring mill, designed for larger or heavier components. The mill's rigid frame accommodates extended cutting forces, allowing deep bores and flat surfaces to be machined with minimal vibration. Operators input program parameters, and the milling head executes multi-axis movements, producing perfectly aligned holes, counterbores, and recesses. The precision of linear guides and backlash-free drives ensures every cut meets design specifications. Watching the machine cut large steel blocks into finished components emphasizes the interplay of forces, material behavior, and machine rigidity in achieving dimensional consistency. Coolant pressure is precisely regulated to avoid thermal expansion during long cycles, ensuring repeatable results. Automated probing checks critical dimensions mid-cycle, reducing the need for manual intervention. Inspection follows, with calipers, micrometers, and CMM probes confirming tolerances, surface finishes, and alignment. Any minor deviations are corrected through controlled secondary machining or adjustments to program offsets. It is striking how the combination of CNC automation and skilled operator oversight results in parts ready for high-demand applications in oilfield and industrial equipment. Finally, completed components are cleaned, deburred, and packaged for delivery. The process demonstrates a seamless flow from raw stock to finished precision parts, reflecting the integration of multiple advanced machining technologies. Each stage, from twin-spindle turning to horizontal boring, contributes to parts that meet rigorous industry standards. Observing these operations offers insight into modern machining capabilities, revealing both the power of automation and the skill required to harness it effectively. Temperature-compensated linear encoders ensure every part remains within specification, even after extended operation. Surface roughness measurements validate that finish quality meets client requirements before shipping.
The concept of pressing alloys from every side may seem simple, but in practice it requires massive equipment and exact control of force. Instead of relying on a single axis of pressure, it applies power from 4 directions simultaneously, shaping large billets with remarkable uniformity. The sight of massive steel being pressed evenly on every side feels both powerful and purposeful. The process begins with the billet being positioned inside the forging zone of the hydraulic press. Here, 4 opposing dies close in around the heated metal. With each stroke, material is compressed radially, reducing cross-sectional thickness while maintaining length. This technique ensures efficiency, as deformation occurs quickly without excessive reheating. As forging continues, the billet is rotated between strokes to guarantee symmetry. Each adjustment helps distribute strain evenly, avoiding cracks or defects that could compromise performance. The result is a dense structure with consistent grain flow. One cannot help but admire how such controlled steps can turn raw strength into structured form. Hydraulic presses used for this process can reach forces up to 125 meganewtons, allowing the treatment of exceptionally large parts. This magnitude of power makes the device suitable for industries requiring heavy shafts, tubes, and other components. The scale of force involved highlights just how advanced forging technology has become. Final passes refine the shape, producing near-net dimensions that minimize the need for subsequent machining. By using 4 dies instead of 2, material waste is reduced, and productivity is significantly increased. It is impressive how engineering choices at this stage directly influence cost and material savings. The finished forgings leave the press with improved strength, structural integrity, and dimensional stability. What once entered as a rough billet now emerges as a high-value component ready for further processing. Such a transformation reflects the union of mechanical might and engineering design. The scale of steel fabrication for large industrial tanks always carries a sense of awe, and here the focus is on a 100 cubic meter capacity vessel. Each stage shows how flat steel sheets with thicknesses of 6 and 8 millimeters become cylindrical sections that will later be joined into the full body. Even at this opening moment, the sheer size of the material feels powerful. One can almost feel the weight of each steel sheet even before it moves. The workflow initiates with steel plate preparation. Sheets of the specified thickness are measured, aligned, and readied for rolling. Mechanical handling systems support the weight, ensuring that every plate is positioned correctly. Attention to detail is critical. A minor misalignment could ripple through the entire tank. The raw steel holds potential, waiting to be shaped into something with strength and function. The enormity of the sheets demands respect from anyone nearby. At this point, every detail matters, since an error in alignment could affect the entire tank. Watching the plates being readied, one appreciates the engineering behind their support systems. Each adjustment of the plate seems to carry the weight of the final vessel. Rolling comes next. The plates are fed into large bending rolls that gradually curve the flat sheet with a diameter of 200 millimeters. The steady hum of the machinery emphasizes the scale of the operation. The machine applies consistent pressure across the surface, creating a smooth arc until both ends of the plate meet. Flatness transforms under force, hinting at the future volume of the tank. It is striking to watch flatness transform into curvature with such force. Observers might note the balance between machine power and material resilience. Every pass of the plate through the rollers shapes not just steel, but the vessel's eventual presence. Even small variations in rolling would be immediately apparent. After rolling, longitudinal seams are welded. Automatic welding systems travel along the join, producing a continuous bead that seals the cylinder. The glowing welds illuminate the intensity of each stage. Each bead reinforces both strength and structure, crucial for a 100 cubic meters tank. It's fascinating how human oversight ensures the weld maintains uniformity along the seam. The precision of automated welding ensures not only speed, but also uniform strength across each seam. One cannot help but admire the synchronization of welding and handling. The cylinder begins to feel like a tangible component of the massive tank to come. The finished shells are then assembled. Cranes lift and align each cylindrical section, stacking them to build height and volume. Steel takes on the promise of motion as a hydro-turbine runner is prepared for machining. The initial focus is on forged and cast blanks, chosen for their strength and wear resistance. CNC machines remove material layer by layer, shaping complex blades designed for fluid efficiency. It is impressive to see how calculated movements of cutting tools translate raw metal into a form optimized for energy capture. HVOF coating is applied, enhancing durability and anti-corrosion properties. Testing and inspection ensure all dimensions and surface qualities meet rigorous standards. The finished runner reflects engineering mastery, ready to convert water flow into reliable power. A system designed for a Vietnam client shows how speed and control define upright roll forming. The first operation involves steel strip feeding into the line. Rollers then shape the material into upright profiles with steady progression. Every pass through the rollers builds more detail into the section. A flying shear takes over to cut pieces at set lengths without halting the line. The action looks seamless as steel flows continuously. Widths adjust automatically, allowing flexible production. Such automation reduces downtime and boosts consistency. Operators rely on the machine's stability to maintain quality at high speed. What emerges is uniform steel profile after profile, ready for structural use. The vessel pauses as the anchor chain releases in controlled surges, securing the mooring buoy firmly offshore. Heat and movement fill the workshop as massive blanks are prepared for shaping. Giant components, each weighing several tens of tons, are positioned for the first operations. Observers can't help but marvel at the scale and coordination involved. Preparation of the first ring blank opens the production phase. The blank, with an inner diameter of 1,253 millimeters and outer diameter of 3,954 millimeters, is carefully inspected and aligned. Operators measure and verify dimensions before moving to the heating stage. The furnace temperature is closely monitored to guarantee uniform heating across the entire blank. The glowing steel in the furnace emphasizes the intensity of industrial work. Heating brings the blank to the optimal temperature for shaping. Once ready, the radial-axial rolling machine engages, gradually forming the ring over 214 seconds. Height reaches 3,986 millimeters, with a wall thickness of 173 millimeters, while sensors and guides constantly maintain the correct profile. It is impressive to witness such massive components undergo controlled deformation. A larger blank, measuring 1,584 millimeters inner diameter and 1,288 millimeters height, undergoes similar operations. Over 460 seconds, the machine produces a rolled ring weighing 89.3 tons with a wall thickness of 566 millimeters. The rolling action combines radial and axial movements, ensuring uniformity across the enormous surface. Engineers continuously check sensor data to adjust rolling parameters in real time. After rolling, the rings are slowly cooled and inspected. Handling rings of this magnitude highlights both the strength of materials and the skill of the team. The scale and efficiency of operations highlight both technological advancement and human oversight. The factory buzzes with activity as high-speed presses prepare to shape heated steel. The workflow opens with steel heated to 1200 to 1230 degrees Celsius, ready for forging and specialized dies. Watching the glowing metal slide into the molds emphasizes the power of industrial machinery. Forged components are immediately transported by robots, ensuring zero-drop movement between stations. Alignment onto trays is automated, and cameras confirm each part's position. Cold forming follows, with robots picking products from pallets and placing them precisely for the next step. High-speed presses then complete the final shaping of gears, shafts, and automotive components. Finished items are prepared for packaging and shipment, demonstrating a production system capable of rapid, accurate manufacturing while handling complex forged parts. Reactor pressure vessel is carefully lifted and positioned at root per NPP. Cranes coordinate each movement, ensuring alignment with the containment structure. The scale of this operation impresses engineers on site.